Good afternoon, folks. Welcome to Olympus's Inspection 360 webinar this afternoon. We should have a really good talk ahead of us here, and I appreciate you all joining. I did want to just show you here briefly how you can interact with us. There are several different ways. In the main portion of the screen here, you'll see our slides in just a minute when when Dr. Gasly is presenting. There are also some resources over on the right-hand side with additional information about portable XRF and its applications in mining. And then down below, if you click in the middle, there's a section for attendee chat. We'll have a live chat going on. You can post your questions at any point or discussion. I'm Michael Hall. I'm one of the X-ray specialists at Olympus, also product manager for the Americas. And I'm going to be monitoring the chat and sort of emceeing today's discussion. So feel free to open up that chat window and put discussion in. We're going to have lots of time at the end for question and answer, but feel free to just go ahead and put your questions in real time as they come along. So I want to introduce our speakers today. Again, I'm one of the X-ray specialists. I'm Michael Hall, one of the X-ray specialists with Olympus. Joining me from Olympus is Todd Houlihan. He's our International Mining Director, supporting our partnerships and collaborations with the mining industry all around the globe. So it doesn't matter where you're joining us from today, we've got a really strong technical team to help support you. And then headlining for us today is Dr. Michael Gasly. He's a principal consultant and principal geochemist for RSC, and he's going to share some about his history and some current projects that he's working on, give us some perspective on using portable XRF for gold exploration and mining. So thanks again for joining us. I think you're going to find this worthwhile today. If you're new to portable XRF, if you're not familiar with X-ray fluorescence, we do have lots of places in the mining life cycle. We're going to talk mostly about gold today, but for all types of mining, copper, base metals, platinum group metals, there's solutions throughout the mining life cycle from prospecting to exploration, processing, refining. So feel free to see some of the resources on the right-hand side there in the webinar platform, or to hit up our website to hear more about those things. But we're going to focus primarily on gold today. You can sort of think about the evolution of portable X-ray fluorescence as sort of going parallel with the evolution of a lot of other portable technologies. And I've used here the example of what used to be called personal digital assistants, or Palm Pilots was a name brand, and now more commonly, smartphones like the iPhone or Samsung and that sort of thing. And so, Olympus had its first portable X-ray fluorescence instrument in the early 2000s, the Alpha. Okay, this was again in what I would call the PDA or Palm Pilot era, and this technology has evolved over time in much the same way, parallel to sort of improvement in processors and solid-state memory that's happened for the smartphone industry, getting us to where we are in sort of fourth generation technology with the Olympus Vanta XRF today. And there's been developments in the processors, in the detectors, from sort of low resolution silicon pin detectors to high count rate silicon drift detectors to sort of ultra high count rate or ultra low noise silicon drift detectors in the latest generation. Again, parallel to the way we've seen an evolution in, say, cameras on smartphones. And parallel to the improvement in the hardware has been improvements to the quality of the calibrations, from sort of very rudimentary mathematical methods, Compton normalization, to very sophisticated multi-beam fundamental parameters, first principles physics types calibrations, what's sort of often referred to as mining or geochem calibrations in the marketplace. So some of you have been around for this ride of evolution from the beginning. Some of you may be joining very late. I want to just, for perspective, hand it over to my colleague Todd Houlihan. He's been here for much of this ride and can share some of the historical perspective on this evolution. Todd?
Thanks very much, Michael. Can you hear me okay?
Yeah.
Okay, good one. Welcome, everyone. Thanks very much for your attendance. So, just a bit about my background briefly. I'm Australian. I live in the UK at the moment, but studied an applied science degree in environmental management at the University of Newcastle in Australia, and then spent the next 7 years working as a contaminated land consultant. And that's where I first got my first experience with portable XRF, cleaning up a lead contaminated site in Sydney. And as a result, I went to work for a company called JBS, which was an environmental consulting company doing contaminated land investigations, but also had the distribution rights for the early Niton portable XRFs. And in that time, we gained a lot of experience using the equipment and developing methods to get good data. After that, I went to work directly for Niton in Europe, looking after Europe and Africa. And then they were taken out by Thermo in 2008. And at that point, I came over to Innovex, which became Olympus. So I've been with Olympus Innovex now for the last 13 years, looking after the global mining industry. So that's 21 years now I've been working directly with portable XRF in the minerals industry. And so before we start talking about how XRF got to the point where it is now in being used routinely in the gold market, I wanted to give a bit of background and point out that really when I first started working in this industry in the year 2000, it was from that contaminated land perspective. And even as early as the mid-90s, the United States Environment Protection Agency had written a method, US EPA 6200, for using portable XRF for contaminated sites. And so that's one of the reasons why some of the early instruments had a soil mode, what we would call a soil mode, because the original modes on these instruments were designed for contaminated sites. Now, it's important to point out at that time, gold was about $300 an ounce, a real low point. So there wasn't much happening in the gold market, and detection limits were obviously rather high. But one of the landmark points in the evolution of this technology was a large project done in Broken Hill when the company Perilia took over the Broken Hill lead zinc deposit from Pasminco and needed to do a baseline soil survey of the entire town. And they chose portable XRF to do that, and they chose JBS, the company I was working for. And so the New South Wales Environment Protection Agency signed off on portable XRF being used as the principal analytical tool to assess the contamination of the entire town based on 100 years of mining, the line of lode, which runs through the middle of the town. We also assessed 100 residential properties as part of that, lead in paint, lead in ceiling dust, lead in vacuum dust, lead in soil. And that was a real landmark moment in the evolution of the technology because it enabled a lot greater visibility into the mining industry on the capabilities of the equipment. And 10% was sent off for nitric acid digest at the lab and 10% was sent off for hydrofluoric acid digest. And the results came back almost exactly the same. And so around that time, the 2002, 2003, we started publishing a lot of papers. We were doing a lot of work, but the industry wasn't quite ready for such a radical tool. No one thought a small little handheld instrument could do what we were saying it could do. So we started publishing a lot of papers at my Aussie Mine Geology Conference, at the International Geochemical Exploration Symposium, and it really started to gain traction because the science was so robust. And at that point, the early exploration adopters started to get involved, based on those elements that we had proven in the contaminated land industry worked really well, namely lead, zinc, arsenic, nickel, copper, all elements that we were proving were performing excellently. And so it was around that point that some of the more innovative junior explorers were coming on board, people like Ian Pringle, Alastair Cook, and another landmark moment was the CSIRO in Australia, Charles Butt, Ravi Anand, some of the work that those guys did around 2003, 2004, who were gold guys, and started to realise that, okay, we might be able to use this copper, this arsenic, this lead and zinc as a pathfinder tool in the gold exploration business. And so it wasn't really, and so that took a lot of time to bubble up and give it some more credibility. And so it really wasn't, I think 2006 is quite an ambitious, when I tried to recall this timeline, it really wasn't until about 2008, 2007, 2008, when really the mid-tiers and the major mining companies like the names you can see on the screen really started to adopt the technology, do their own evaluations on their own samples, compare the results with the laboratory. And so this is my lead in to Michael. I think, Michael, this is about the time that you started to get involved in portable XRF. And so I just wanted to give that background to where you come in, really, and your experience with the technology. So I'll hand over to you now, Michael.
Thank you, Todd. Yeah, I'll just, we want to tee up here with for Dr. Gasly. I mean, he's been, as Todd said, sort of coming onto the scene in his own work in the mid 2000s. Most of his schooling at Victoria University of Wellington, and then geologist at Barrick. So obviously a strong background in gold. And then moved over to CSIRO, for the Commonwealth Scientific and Industrial Research Organization, and strong research and publication record during that time, tied to portable X-ray fluorescence, which I'll show in just a minute, and then now is over at RSC. And so if you look at Dr. Gasly's publication record, this is just a selected bibliography, but a couple of things stood out to me. Obviously, a lot of work in gold mining, gold exploration, so plenty of deep experience with that. But also, if you look at some of his early publications, a lot of work on establishing the quality and reliability and best practices of portable XRF. And so you see some of his early papers here, a review of the reliability of portable X-ray fluorescence, or is there reliability and validity in portable X-ray fluorescence spectrometry. And what I noticed is over time, these questions about the reliability or the trustworthiness or the value even of portable XRF, those questions have sort of faded away as this has moved towards a more mainstream and accepted technology over the last decade and a half or so. So I'm very pleased to have Dr. Gasly with us today to talk a little bit about some of the projects he's been involved on in the past, his experience with portable X-ray fluorescence, and some of the exciting opportunities he's involved with now. So thank you, Dr. Gasly, for joining us, and we'll look forward to what you have to share with us today.
Cool. Well, hopefully you can hear me.
Yes, we can.
Excellent.
Go ahead.
Well, look, excellent. Well, like you said, Michael and Todd, I started playing with portable XRF in about 2007. As your timeline kind of wrapped up there, Todd, segueing into what I'm going to, talk about, kind of here today. And, I was at Barrick, as you noted, and I was given a portable XRF instrument and basically said, go forth, make numbers, do something cool with this thing. So I've probably made just about every mistake in the book, and hope that I am not going to repeat those anytime soon. And, I want to share some of those learnings and try and, basically try and convince people that, portable XRF we should regard it as normalized. It's here, it works, and with a bit of a care, you can generate some really cool data that you can do a lot of cool things with. So with that in mind, I want to dive into the physics of portable XRF for a minute, or X-ray physics more broadly, actually, because we actually understand it really, really well, and there shouldn't be any surprises. All the things that we see, as I'll show some examples in a minute, we can model, we understand. So the way the X-rays interact with anything you put in front of an instrument, we have a pretty good idea how well that's going to work. I want to make some comments around the quality of portable XRF data. I could put plot after plot after plot of lab portable XRF geochemistry data, but they all look very much the same. By and large, when the data are collected, with decent protocols, decent workflows, and appropriate standards, and then the data are treated appropriately, you finish up with really nice comparisons to the lab. Then moving into the gold space, I want to make some comments around the mineral exploration end. What's a geochemical anomaly, how we might go about finding it, how XRF can play out what I think is a really critical role in that, by generating really large data sets in locations where getting samples to the laboratory quickly or even at a sensible cost could be difficult. Then I'll make some comments around portable XRF in the mine environment, and then finally some comments around gold by portable XRF, because that's the thing everybody always wants to be analyzing directly. So the physics of XRF are really well. On the next slide, I have a table of X-ray peaks, and we know what elements are with which elements, and thus which are problematic, and which you might need to work harder on to deconvolve. And I think that's something that comes back to the evolution of technology, that Todd was alluding to earlier, and those algorithms getting better through time, that all of these interferences, these well-known physics problems, are getting solved better and better and better as it goes forward. You see like the cobalt deconvolution algorithm coming out, from Olympus, where we're getting cobalt, probably traced to minor element that's got a peak interference with iron, so a major element. Like what we have here. Here are some peaks that pile up. We've got sulfur, moly, and lead. They all sit on top of each other. So you could imagine if this was the only bit of the spectra that you could see, the only bit that you were able to detect, you'd struggle to quantify how much moly, sulfur, or lead was in any given sample. These things are known, like I mentioned. I've got to use the click button to advance my slides. There we go. We have tables of all the elemental interferences, all the different interfering on each other for the different elements. And as I just had as my example there, come on, animation, there we go. Sulfur, moly, and lead are all listed there. And this peak at about 2.3 keV, kilo electron volts, is where we have this interference happening. And you can work your way through the whole periodic table and find all the elements that interfere on each other. So there shouldn't really be any surprises when you say, is the data for, I don't know, pick an element, gold any good? You can go and find gold on this table, and you can go and find that arsenic and tungsten and zinc all interfere with it. So if you want to make a reliable method to quantify gold, you'd need to be thinking about how you dealt with those elements. So like I say, shouldn't be any surprises there. If we think about the physics of actually getting X-rays, from an X-ray tube to a sample and back to a detector, we can model that. We can model how far X-rays transmit in air. Here's some modeling that I did a few years ago, where I was looking at how many X-rays would get across a 1 centimeter air gap. So basically, you have 0% transmission at the bottom of the plot there, and on the y-axis, and 100% at the top. So across this 1 centimeter gap, if the line's at the top, all of the X-rays have made it across. And along the x-axis there is photon energy. So that basically relates to the different elements. You can see I've labeled some there. Sodium, just over 1 keV, magnesium a little higher, and calcium at 3.7 keV. And if you look at how many X-rays make it across that little air gap, for sodium, for 1 centimeter air gap, you only get 3% of those X-rays across. For magnesium, a few more, it's 9%. For calcium, it's about 88%. So this is telling us why we struggle with atomically light elements, because just the fundamental physics are problematic for us. The X-rays that are produced when you excite that sample with an X-ray beam just don't transmit very far through the air. So you're going to need to be analyzing for much longer and thinking about other problems like what you've contained your sample in. So, oops, I probably just clicked twice and put 2 plots up, but that's all right. I'll go back one so we can see the key for the middle one here. So again, the same modeling I've done on panel B there, but this time, instead of trying to transmit across 1 centimeter of air, I'm looking at how many X-rays make it through a given material. So the orange line is 4 micron mylar, and the blue line, or the purpley blue line, is 4 micron polypropylene. And we can see here that just by changing the nature of the material you cover the sample with, still 4 microns thick, but just going from polypropylene, which I think has a density of 0.9, to mylar, which has a density of, I think it's 1.4, you finish up with 1.7 times more X-rays on the magnesium peak coming through. So when you're thinking about, how am I going to analyze my samples, what am I going to put them in, these kind of considerations really matter. And then you can take that forward in my final piece of modeling here, where I modeled what would happen if you analyzed through 65 micron thick paper. So that's kind of like a typical bag that you get your geochemical samples back from the laboratory in. And then I've also modeled 200 micron calico, kind of if you put your samples into a, say you're drilling an RC and you put your samples into a calico bag and you want to get some quick analyses and you just analyze straight through the paper bag, the calico bag. And I've shown here calcium and iron. We'll look at calcium for a moment. You can see that the 200 micron thick calico, for calcium, you're only getting 4% of the calcium X-rays through that calico bag. So basically, if you're going to analyze samples through a calico bag because you want some kind of quick analysis of how much of whatever element is that you're chasing that's in there, if your element's atomically lighter than calcium, you can forget it. All of those X-rays are going to be absorbed by the calico. If you look at the 65 micron paper, about 32% of those X-rays get through. So you might be able to quantify calcium okay, but then you start to have problems that there's possibly calcium in the paper bag that you're analyzing through. And this kind of provides us with a tool where we can decide where we are able to use portable XRF, analyzing through these different sample media, what might be reliable and not. And it kind of goes to my point of, there shouldn't be surprises. We can model this. If you go and analyze, say, copper, you want to know copper grades, and you analyze through a paper bag or you analyze through a calico bag, you're probably going to get some fairly okay results because copper is a little bit atomically heavier than iron, so its X-ray transmission is a little bit better. So you should be getting, 60, 70, 80, maybe even 90% of the copper X-rays through those materials. So you should be expecting to get low values, but they should be, varying and reasonably well quantified compared to the values that are, actually in the sample. I'm sorry, I mean varying is that you're actually going to see changes. So, there shouldn't be surprises here when we put different sample containers, I guess, between the sample and what we're analyzing. We can do exactly the same thing with altitude. Basically, when you go to high altitudes, you get more effective X-ray transmission. There's less, oxygen and CO2 and nitrogen molecules to get in the way and slow down the X-rays. And we can model that on the left. I won't go into it in detail. But that means that actually, as the panel on the right shows, that you can actually apply a correction factor to take that into account. And there's a couple of data sets there, 2 instruments that have a pressure correction built in and 2 that don't. And basically, the x-axis is showing what happens as you go to higher altitude. The far side of the plot's about 6,000 meters at 400 millibar, and I've just presented it as a normalized silica concentration, basically showing that if you start out at sea level, you have a value of 1. If you go up to 4.5, 5,000 meters, you're going to be getting 1.5 times the counts of silica because there's less, the air's less dense. So you're going to finish up getting higher silica values. Now, why does this matter to us? Because if there's not a pressure correction being applied in that instrument automatically, those increased silica counts are going to flow into your trace elements because everything's normalized to 100%. It sums to 100%. You increase the silica content by 50%, 1.5 times. You must decrease everything else. So this is where, if you're wanting to monitor, say, arsenic concentration or something like that as a pathfinder element, you might find yourself running into trouble if pressure correction is not being applied, because those concentrations will decrease if you analyze the sample at 4.5, 5,000 meters versus down at sea level. So again, no surprises here. The physics are well known and pretty clear. So, jumping on to the quality of the data, I just want to make some comments here that we need to make sure that we are comparing the correct analytical method with portable XRF data. On the left plot there, the green data set is a soil sample data set, portable XRF versus 4-acid digest, and that's a pretty good correlation, approaching 1-to-1. I think it's got a slope of about 1.06, so we're pretty close. But then the pink population is compared against aqua regia, and you can see that that's a partial extraction. It's only getting about 10% of the rubidium that's actually in those samples, and you get a really poor relationship there. And if you were to only compare your portable XRF data to aqua regia data, you'd go, well, this is not very good. What's going on? And that's going to vary by analytical method, by and by element. So you do need to have a little bit of care there in picking that. You're comparing the right element with the right element. On the right-hand side there, you've got some plots of zirconium against different analytical methods. The top 2 panels are 4-acid digest. The black line is the 1-to-1 line. And we're only getting about 25% of the zirconium out of these soil samples that we've analyzed by 4-acid digest. Compare that to flux fusion or laboratory XRF, the bottom 2 panels, and the portable XRF is actually comparing really favorably to the laboratory data. I should point out that the standards that we use to establish that correction factor, the highest zirconium concentration one was about 600 ppm, and that the instrument is reporting a little bit low compared to the laboratory. So again, 2 examples here of just making sure that you're comparing the right lab method with the right with portable XRF data, so that you are actually comparing apples with apples.
And Michael, you've selected zirconium and rubidium presumably because they're immobile and good to be used for lithogeochemistry applications in identifying rock types, right?
Yeah, absolutely. Rubidium here, I'll be looking, rock types in, felsic rocks or metasediments. Rubidium's one of my go-tos, but also, rubidium for alteration, rubidium-strontium ratios are really powerful for mapping hydrothermal alterations. So really important elements in that space. And yeah, zirconium from a lithogeochemistry point of view. And it's typically one that I see people point to as not being that good, where actually from a physics point of view, it's one of the best elements to analyze by portable XRF, because you get beautiful excitation off a 40 kV or 50 kV beam on zirconium. It's kind of sitting in a real nice sweet spot you're going to test me now, what's the extra energy? It's somewhere around 16 keV. So you're getting about 3 times the excitation energy on the peak that you're trying to measure, and you get optimal excitation, basically. So it's a really beautiful element to use. And the problems are actually around the comparison data set, typically. Not so much the portable XRF data itself.
Yeah, they're all doing 4 acid and they're all doing 4 acid and atomic absorption or aqua regia, and it's not up to the job sometimes, right?
Yeah, exactly. And often what you find is that the 4 acid digest will manage to get maybe 150 ppm of the zirconium out of the sample. Sometimes you see a hockey stick kind of shape where it will go up following the one-to-one line quite nicely, and then it will get to about 150, 170 ppm zirconium, and then just not able to extract anymore, not able to dissolve any more zircons. And that gets to be an even bigger problem in soil samples, where those zircons have been kicking around on the surface for some time, and any vaguely mobile zirconium has been taken out of them. So it can be even harder in soil samples. And also, reference materials. Sometimes you struggle to find reference materials that have been analyzed by flux fusion, so you can have a really nice zirconium value to actually calibrate your instrument against. So some challenges there, just things to watch out for. But all the multi-element data can be incredibly useful, and like I say, carefully corrected, really powerful. And I just want to also make the point that when you do things carefully, here is a comparison of portable XRF data against lab data, and you can see something's gone a little bit wrong in the zinc plot on the left-hand side there. And we're looking at zinc between about 40 and 120 parts per million, where that little subpopulation has pulled away. And what that actually was when I went back to the laboratory concerned, the ICP MS had lost its calibration. And it wasn't a portable XRF issue, it wasn't a lithology issue or a matrix issue. It was actually a laboratory issue, 4-acid digest ICP MS data. Like I say, we're at pretty low concentrations there, and we are able to see whether the lab had an issue. So definitely utility, and I'm just chucking this up as I guess an example of how consistent you can be when your data are carefully collected and carefully corrected with good standards. And then to try and pull us together, it's a theme I'm going to try and push a little bit more at the end, is I really want to see us as a community normalize portable XRF data. To me, it's just another tool in the toolbox. And here are 2 papers that I published recently, 2019, 2021 economic geology and ore geology reviews, where portable XRF data was used and there was no laboratory data set to compare them to presented. Portable XRF data was just used as part of, as another tool in the toolbox, like using a hand lens to identify minerals or, thin section microscopy. We just used portable XRF, we presented the data, we said we'd collected it with standards and corrected it, and put it out there, and there was no challenge whatsoever from the reviewers. So I think we've kind of hit this critical point in the community where you can collect and present portable XRF data, and if you do it properly and can show people that you've collected it properly, there really is no challenge and no issue anymore. So I think we've come a long way from kind of 2007 when I started out, where very much skepticism. 2012 to 14, where the Camaro study and Gwendy Hall and the work of CSIRO as well, Louise Fisher and others were really working through analysing a heap of standards to understand where the instruments are good or falling over at that time. And now I think we've really reached the point of normalised use, that they're just another tool in the toolbox. So this slide actually provides a nice segue into where I want to go to next. I want to go and explore that Ore Geology's reviews paper a little bit and present a case study of mineral exploration. And if the taste that I've given you here gets you really excited, there's shortly going to be released a almost 40-minute version where Todd and I have a chat about this case study in much more gory detail than I'm going to present today. That will be available online shortly. So, yeah, I guess when we're thinking about geochemical exploration or geochemical anomalies in mineral exploration, say you're looking for a gold deposit and you want to find an arsenic anomaly, or you want to find a copper anomaly, or whatever it happens to be, there are going to be, if you're going to go and collect a massive soil sample data set, which is what we're going to talk about here, the data set's got about 10,000 portable XRF analyses in it, and it's got about, and the gold in this data set is collected by Ecoregia Digest. So if we're thinking about what is driving the chemistry of those soil samples, there's going to be three things, I think. There's going to be the background, or the natural elemental content of the rock from which that soil was derived. There'll be any metasomatic or hydrothermal or mineralizing process that has perturbed or changed the natural element content of that rock. And then there'll be some enrichment or depletion of those elemental concentrations when the soil was formed. So as explorers, we want to try and find number two, the metasomatic or mineralizing processes. Excuse me. So that's just what I want to have a quick look at in this case study and kind of show you how far I think you can push portable XRF data. The case study is in Eritrea, so that's north of Ethiopia, sitting against the Red Sea in the Nubian Shield. I need to thank Alpha Exploration for letting me present this case study. We're in an area called Kakasha, and we've got a bunch of granites and volcanoclastics and mafic rocks and metasediments across this license area, almost 1,000 square kilometres there. And we have this map as mapped by geologists, and you can see there's that beige that kind of covers the middle of the map. 39% of the map is covered by cover, jello, soils and colluvium and things like that. So we can't really see what's there. We can make some inferences, but we're not certain. So as I mentioned before, this area is now covered by soil samples. I'll show you the map at the end, but it's got 500 by 500 regional grid and then a whole bunch of 100 by 100 local infill grids. As I said, more than 10,000 samples. I think it's now probably about 15,000, 16,000 in this data set, all analyzed in the field, in the field camp. Samples were collected, dried, sieved, and then analyzed, and the data are all corrected using the workflows that we've generated over the last decade or so. As I mentioned, we want to try and understand what the background elemental value is of the any soil sample at any point. So we had that previous map that was as mapped by the geologists. This map here has been mapped using machine learning. You can read all the gory details about that in Sean Hood's paper that came out of his PhD. Where we've just taken that same bedrock map, used the geophysics, the radiometrics, the magnetics, and so on to try to generate a better bedrock map. And if I just flick between the two of them, you'll see that actually the map patterns are very similar, but now we can make some classifications of the lithology that are under those cover. And we can also be probably more objective in how things are classified. So now for any given soil sample in that whole field area, 1,028 square kilometres, we can objectively classify what the bedrock is that's associated with it. Next, so that's that point there. We've now sorted out the background or elemental content of the rock. The next thing we want to try and do is understand what the soil sample is. The soil type is, or regolith type is at any of those soil samples. People are not necessarily that great at always calling the same thing, especially if you have multiple teams out in the field collecting soil samples. One person might call it colluvium, one person might call it alluvium, one person might call it mafic derived, one person might call it felsic derived. What we have here is another machine learned product. Took the ASTA satellite spectral data, ran it through an unsupervised clustering algorithm, and you can finish up with this map. We can then look at what we know about the local geology and derive some soil classes. Like light blue, for example, is in situ felsic rocks. The green is in felsic in situ mafic rocks, the yellows transported mafics, and so on, and the blues and reds are some of that cover. Now we have a classification of soil type at any given point. So if we have these two things, we can look at some clever statistical ways to try and derive that metasymmetrical mineralizing process. So what we can then do is take all of those soil samples and start playing around with that. Here we are looking for a copper-gold or a gold-copper, depending on where you are in the system, mineralizing style. So what I've done is I've normalized against the bedrock type, normalized against the soil type, and now we can make some polymetallic indices. So this here is copper from the portable XRF plus gold from the Acregia data at the lab. So really big data sets. As I said, about almost 10,000 data points when I made these maps, now 16-odd thousand, all analyzed in the field. Some portion of those, varying a little bit depending on what program we're at, go into the lab for acid digest for comparison. But just the ability here to generate data quickly to enable the guys in the field to follow up without having to wait for samples to try and get back to Asmara and out of Asmara and then over to Ireland to be analysed was really key. And also the cost. The cost of shipping samples out of Eritrea is fairly high. So only having to send small amounts of samples and only having to send samples that we actually really knew needed to be analysed was pretty key here. So the multi-element data was all off portable XRF, so just huge data sets, and I think that's a massive opportunity for us as we move forward. Generating data sets that are potentially cost prohibitive. So now I just want to jump to the mine environment. One of the other quite useful advantages of portable XRF is that we can collect data directly on drill core. Here's an example of 5 drill holes collected over 2 kilometres at Plutonic Gold Mine in Western Australia. Data out of my PhD. Data collected directly on the drill core, just wandering along, collecting 1 metre spaced analyses, normalising it to make sure there's no analytical drift in the data, and then plotting it up. Red is chrome, blue is titanium, yellow is zirconium. You can see some really useful trends in there in these mafic rocks. And I've lined them all up on one of the metasedimentary marker units on that purple line with the black stars. So, to go back to 10, 20-year-old drill core and resample it for multi-element analysis at the lab probably wasn't going to happen. There's a lot of meters of drill core there, but just wandering down the drill holes with a portable XRF instrument, definitely easy to do. So here's an example of a value add that you just couldn't, probably or potentially justify. Certainly when you're starting out, if you found it was really useful information, then maybe that is the point to justify some laboratory multi-element data. But as a first pass data set, really useful. So building on that data set, one single fence, we're going still back in 2011 when I was at Barracks, still at Plutonic Gold Mine in Western Australia. Here is just that chrome data plotted within the mine mafic package, the mafic rocks that I mentioned before, high chrome near the hanging wall, getting to lower chrome near the footwall, and then those drill holes that have got the little orange bit, little red bit at the bottom, that's punching back out into the footwall ultramafic. So again, being able to generate really big data sets that cover large areas is really, really important. And in a mine environment, the samples are probably going to be analysed for gold by fire assay anyway, so you have a nice pulp sample to analyse when it comes back from the lab.
But what was your objective in these cases?
Good point. Thank you. I should comment on that one. This is about lithogeochemistry. This is about what the stratigraphy is doing, what rocks join up with rocks. You can see on the bottom left-hand end there, the package gets a lot thinner, and there was always a question of what kind of fold offset had happened there. It probably belongs at the top of the package, and there's a bit of a down drop block there. The other thing was here at Plutonic, it looked like there was certainly in places a bit of a stratigraphic control on gold mineralization. Different mineralization was being focused on the boundaries of different mafic units. So being able to actually map out the stratigraphy and find those unit boundaries was pretty useful for predicting where gold mineralization might be.
Right.
Then moving further along the mining value chain, I guess, and now we're going to look into the geometallurgy space and starting to plot up arsenic and gold data spatially. High arsenic mineralization, certainly high arsenic mineralization with low gold is not necessarily the stuff you want to be chucking into the mill, because we knew at Plutonic where there was high arsenic, we got much poorer recoveries. So trying to forewarn, doing some geometallurgical domaining up front to be able to improve recovery by improving the processing and blending and those kind of things at the plant. So here we are taking portable XRF data further down the mining chain. And the final example in this slide is arsenic grade shells. So gold grade shells colored by arsenic, showing that if you had lovely recovery up in the top, the higher levels here where there was not that much arsenic, as you kept mining downwards, you're going to get into a zone that had a lot more arsenic in it down the bottom of the image there. So that was a bit of an early heads up that there might be some metallurgical challenges here. Two more examples, just briefly in the mine environment. I want to get over to some chat and that kind of side of things. So here we are at the Macraes gold mine in Otago in New Zealand. Portable XRF data, rubidium potassium plot, being able to break out P-lights from Samites fairly effectively. Here that differentiation is quite important because the Samites tend to act much more brittly than the P-lights, and gold mineralization is focused in and around blocks of Samite in the big shear zone. And we found here that the logging tended to be quite sitting on the fence, shall we say. People tended to call things Samite P-light or P-light Samite, kind of in the middle, not really going to the end members of Samite and P-light, which when you did that, you actually got a much better classification, a much better ability to model some of this stuff up. So quite simple plot, but quite a significant outcome. Another very brief example here with a little bit of multivariate data analysis chucked in. This is from a copper porphyry system in Southeast Asia. I think there's about 13,000 data points in this data set. This is just one little view of it. Chuck some a principal components analysis with some clustering on it, and then plot those clusters up spatially. And you can see that, well, I won't go into the detail, but basically clusters are hanging together. The colored data points are hanging together spatially, which means you've modeled something sensible in the lithologies or the alteration that's going on. The data points are scaled by gold, so you can see the high golds there sitting in the middle of the system around the pink and orange clusters. So something interesting going on there. Like I say, I won't go into the details, but these are the kind of things that you can start to get at with portable XRF data, multi-element data. And this here is around trying to predict, what the lithologies is, what the alteration are. How can we extract more value? Potentially some of those other things, geometallurgy, dropping out as well. Sorry about the quality of the image on this one. It's not that great, but just looking at gold by portable XRF for the last two slides. Here are some data from gold bars from the Olympus methods note that I borrowed these plots from. I have my own data that supports this, just not quite as much. So this is a better example, but certainly consistent with my own experience. You point a portable XRF instrument at something that's basically just gold and silver, and it actually does a really good job of telling you how much gold and how much silver are there. The physics is simple. There aren't the other problem elements that I mentioned before, like zinc and tungsten and arsenic, that are going to interfere. So some really nice relationships between gold by fire assay and gold by XRF and Dore or gold bar data here. And finally, some really recent data using a calibration that Olympus shared with me and Lauren Farmer at Reefton Goldfields here in New Zealand to play with, where we are analysing gold directly in drill core pulp samples that have got high arsenic. So typically a element that would basically make gold very difficult to analyze. You can see that there is over 1% arsenic in a lot of those samples. that's on the table on the right-hand side there, and getting a slope of those data coming out at fairly close to 1 and an R-squared, about 0.99. So concentrations there are kind of above 3-4 ppm, starting to be able to quantify reasonably well. It's a really small data set. Still, we've got a bunch more work to do here, but I think it's really exciting to see these, as I mentioned earlier, cobalt on iron interference being able to be stripped out. It also looks like there's some good potential here in stripping gold off the arsenic peak, which will be really great. So more work to go here, and I might let Todd comment more around this briefly as well.
Yeah, well, I mean, everyone's probably asking, sitting there saying, well, what is the story with gold? How does portable XRF do on gold? And because there are so many interferences, it's in a very crowded area of the spectrum. And Michael Hull, please feel free to contribute your comments here. It's always been a big challenge, detecting gold accurately in a sulfide, particularly with arsenic, with iron, with zinc. Has always been really challenging. So in a quartz vein, different story, because it's rather simple matrix. If it's well disseminated in a quartz vein, we can do quite well down to 2 grams per tonne, or in a really high silica matrix. But what's been exciting in this recent work that we've done here, albeit in very high grade environments, was we've seen us able to strip out the influence of some of these interfering elements, particularly arsenic, and get relatively good linear relationship. So we do have a lot more work to do, but ultimately the vast majority of our customers, who by numbers the majority of our customers are gold explorers now, gold explorers and miners. The vast majority are using pathfinder elements. They're using arsenic, they're using zinc, copper, lead, antimony, bismuth, and some other elements as their pathfinders, or they're using the immobile elements or other elements, as you showed, to identify lithology, inform stratigraphy, and alteration in that way from an exploration point of view. One thing we might like to make sure we mention is the ability to do gold in activated carbon. In a mine environment, gold on activated carbon is one of the simplest applications of portable XRF. It's outrageously simple because it's similar to gold in a quartz vein, only it's at 300 to 6,000 grams per tonne. Another advantage of that is because they have to lime wash that carbon to strip it out occasionally, we can measure calcium in the pores in that carbon to inform when you need to strip it through acid to make it more porous. So the more and more we work with gold companies who are using instruments in their laboratories, the more we discover about how our instruments have got applications in the mining environment. Flotation samples, silica as a proxy for quartz to inform the grind time of a mill, so many different applications. Michael Hull, have you got something to add there?
Yeah, not much to add. I would just say the activated carbon, gold on activated carbon, was one of the resources there on the right-hand side of the screen for those, if you want to download those. And all these case studies that Todd has just mentioned about, pins and bars and rolls and different role of portable XRF at the mine site is all those things are on the Olympus website.
Very good. Well, I've got one more slide, and then I'll try and pull it together. We understand the physics of XRF and portable XRF, so there should be no surprises in the elements that are good, bad, or otherwise. And portable XRF data are good. They can be robust and reliable for many elements that are so useful to us, across the value chain in mining, particularly gold. Pathfinder elements, and potentially even as we move forward, gold itself. We just have to make sure that they're collected, that the data sets are collected robustly, and sensible decisions around how long to analyze for, sample containers, or standards that are analyzed in the sample stream, all of that sort of thing. And you can do some really cool things by generating large data sets with additional elements that you might not get from the lab. I didn't mention it here, but silica you don't get reported by 4-acid digest, but by portable XRF you do get silica data. So there's a really useful add-on. As I showed you before, zirconium by 4-acid digest, perhaps not so great in many situations, but portable XRF, it should be very good. And you also get rapid turnaround. You're in control of that, what samples are analyzed when and how. Also the opportunity I showed you around analyzing drill core directly to get some early insights into what's going on, to help lithology logging and that sort of thing. And I think fundamentally we should just, as a community, normalize the use of portable XRF. And I've showed you those 2 papers that I published recently where it was just part of the toolbox. There was nothing special said about it, no comments and criticism in particular from the reviewers. So I'm really hot on that point, that we just need to, as a community, drive that. And I think that's kind of a good point for us to pick up the discussion on, Todd, just normalizing the use of portable XRF, making it part of the mainstream workflow.
Yeah, I know when we've spoken in the past about case studies, and you say how you're getting tired of seeing, lab versus XRF plots, and we really want to be moving the narrative more to what's the next phase? What are you doing now with your XRF that moves the narrative on? And I think you've shown with the Eritrean project particularly how combining large portable XRF data sets, doing some statistics with that, and combining that with other data sets would be really powerful.
Yeah, absolutely. And that certainly does bug me a bit as someone who reviews quite a few journal papers in the portable XRF space, because I get so many, because I've published so many, I get so many to review, that I'm probably a bit jaded by seeing, as you say, lab versus portable XRF comparisons going, lead is good and copper is good. And I'm like, we know, we've known that for a long time. And all the things that you said, earlier on, we're going to that, around the Prillier example back from, the early 2000s. And, like I say, it's all about, for me, normalization, just using it as a tool in the toolbox. We're there as far as I'm concerned.
Yeah. I mean, there's that. Sorry, go ahead, Todd.
No, you go, Michael.
Yeah, I'm just going to speak to this idea of sort of plowing over old ground, right? When these sort of XRF versus ICP kind of studies. I wonder, Dr. Gasly, for people who are newer to portable XRF and the use of that, where would you put a good reason for some, strategies or best practices, so that they're not reinventing the wheel on best practices, but can really sort of get a manual or a Bible of best practices for portable XRF and soil and mining studies?
Yeah, certainly. I mean, look, as I've said, the physics are pretty well, pretty clear, and I certainly took a whole bunch of guidance from the archaeology literature actually early on, because they did some really good stuff. Some Speakman and Shackley, I can't remember their first names at the moment, but that drove me in 2014 to write the best practice paper in the context of JORC, the Australian reporting code for resources and reserves. So that's a volume that's out there. Dennis Arnn wrote one at a similar time. There's a couple of papers by Louise Fisher around that time. There's a bunch of stuff around 2014 or so where there was quite a watershed moment, and around as I've said, now normalization, but it's kind of taken us 7 years to get there. That was the start there. So there's probably 3 or 4 papers around that time to definitely have a look at, from Gwendy Hall, Louise Fisher and I, and Dennis Arnn at that time. That's where I'd start.
Great, thank you. And in the context there of reporting data, and maybe you two can speak to this better than I can. One of our attendees asked about using portable XRF data in ASX reporting. Either of you speak to that?
I'm much more comfortable, with JORC. I'm a Kiwi who worked in Australia, so I've been in JORC land and reporting to the ASX for most of my career. I'm very comfortable that so long as you are presenting the QC data that goes alongside your portable XRF data, so that would be some number of samples analysed through the lab. Not a problem. If you want to say I collected in best practice, using best practice as per these guys' workflow, and here are my reference materials to show that my instrument was under control, and so on. I personally don't have a problem with it whatsoever, and I'd refer that person to my Gazy and Fisher 2014, where Louise and I tried to lay that out as best we could. If I rewrote that today, 7-8 years on, I wouldn't change much. So I'm pretty happy that guidance is still very fair. I think there's possibly some more challenges in the NI 43-101 space in the Canadian end of things. But no, to report to the ASX, the correct elements collected correctly with good workflows, I don't have a problem with. That is definitely not a carte blanche statement to just grab a portable XRF instrument and report to the stock exchange. There have been some pretty
horrific
examples of that in the past. Try and be more PC than that, Todd, but suboptimal.
Suboptimal. That's more PC. I think Table 1's really quite good and prescriptive in what it asks for if you do intend to report, and it's really about explaining the method that you've employed to derive data that you're presenting. So it's all about explanation. What samples have you tested? What have been your workflows? What sample prep you might have done? Has the instrument been calibrated? So it's all about as much if you are going to report the ASX, and I'm no authority on this, but I've been around long enough to have seen the good, the bad, and the ugly. It's really about making sure your processes are robust and explaining those clearly.
Absolutely, and I think
just proving that your data, proving by some corresponding laboratory results that the data is solid.
And I'd add to that if you want to have the confidence that JORC was kind of expecting portable XRF data to be reported, the word portable XRF is mentioned in the guidance in the Table 1. It's written there. And that's from JORC 2012. So, 9 years ago, it was kind of, is expected the right word, anticipated. So I don't think there's a problem, and I think people could probably do more than they are with respect to reporting more portable XRF data.
Yeah, we can provide examples of good reporting, not so good reporting, if people are interested in seeing that.
And I would also be cautious about adding some kind of disclaimer language that it is portable XRF data. Just make those statements overt, not implied. I think that would be another key to take out of that.
Yeah, full transparency.
Exactly.
Yeah, transparency on methodology, for sure.
Yes. Yeah.
This is a little different than gold per se, but we did a question about rare earth exploration, using portable XRF for rare earth exploration, and in particular the attendee asked about yttrium, dysprosium, yttrium, uranium, and thorium. And then, of course, there's the early rare earths. And maybe this question needs to be taken piecemeal, as not all of those elements are the same, I think, for portable XRF. It does.
And actually, while we've been having this webinar, one of my colleagues has messaged me almost exactly the same question. How would you use portable XRF for rare earth exploration? And my response was basically I would be focusing on the elements that are telling us something about the system that the rare earths are in, rather than trying to quantify the rare earths themselves, because they're hard. A lot of the rare earths sit under major elements. Things like, calcium, iron, manganese, titanium are all interfering with some of those rare earths that you really want. You can typically get at cerium and cesium. Sometimes lanthanum can be okay. But then I'd be looking at the pathfinders, and other associated elements, things like niobium, rubidium, potassium, barium, zirconium, those elements that we know are associated in those systems, and can be good. There's certainly projects where people have used yttrium and zirconium as proxies for total rare earth oxide, things like that. So it would be, for me, it's about pathfinder. It's about pathfinder elements. It's kind of the gold problem again, right? Find the pathfinder elements, chase them, the ones that we know are robust. And I'll just make a high level comment there that, if you're looking for, say, pegmatites, you're after fractionated granites. So you're after big changes in bulk chemistry. So things like rubidium potassium ratios are really good. So there's certainly tools in the toolbox to unpick that, but it's a bit tricky, and it's certainly a conversation to take offline if that person wants to reach out, because there's a few tricks.
And we should also declare that sometimes it won't work. The same with some
Absolutely.
gold deposits where there are no pathfinder elements. And I did want to tell this story of when I was a young up-and-coming sales guy in Australia, and talking to an old grizzled geologist in Perth about pathfinders, and he said to me, "Todd, the best pathfinder for gold is gold." And it's the truth, and it's a fantastic statement, because there are cases where portable XRF's not going to work in your project, and I want us to be clear that that's also our messaging here. It's not the silver bullet, but there's so many applications that it's definitely something you have to look at.
And if I might add to that, I've never, this is a bold statement, but I think I'm happy to make it, I've never had a portable XRF data set I have not got something useful out of. It might not have been what I went in there looking for, but I always find something, because geology is systematic. Whether I get something about lithogeochemistry when I'm looking for pathfinder elements, or alteration mapping, or geometallurgy, there is always something to be got from having a really good look through all the elements. I'm pretty happy that there's probably 24 to 28 elements that in most geological settings you'll be able to get really decent data for. That is a lot of elements to do a lot of really good, work with. And like I say, it might not quite be what you're looking for. As you say, your story about the best pathfinder for gold being gold itself, couldn't agree more. But you might be able to unpick your lithogeochemistry, your stratigraphy, or something like that gives you the insights as to where the gold is, or is likely to be.
I'm the same with rare earths. I think the same applies to the rare earths.
Yeah.
Yep.
Yeah, we do have a nice cake. Sorry, go ahead, Todd.
Yeah. No, you go, Mike. I think you're going to say the same thing as me about.
We do have a nice case study on rare earth exploration and where portable XRF has strengths and weaknesses there, and touches on some of the literature that you referenced, Dr. Gasly, about total rare earth oxides and some of those pathfinder elements. So if anyone goes to the Olympus website and types in rare earth elements, they'll find that paper, and it ties to some of the literature. And I think a reoccurring theme here, right, is that it's, to Dr. Gasly's point earlier, it's a tool in the toolbox. It's a very powerful tool. It's not a magic wand. It's just a very versatile tool for solving certain types of problems.
Absolutely.
On the topic of gold, we did have a question from our mate Aaron about some of the emerging technology and the portable PPB. I don't know if either of you have any comments on that or had any experience with that.
I'm happy to make some comment to that. It's not dissimilar to your gold and carbon discussion and case study. Basically, you use elixir vivant to concentrate the gold. It's a gold analytical technique, low level gold. PPB is in the name, where you concentrate the gold onto a material. that you can then analyze by portable XRF that doesn't have the interference issues. Its principles are the same. The physics is simple. The chemistry is, pretty well understood. So, as an emerging technology, absolutely. Like I say, physics and chemistry, they work, they're understood. So no, I have no problem with those data whatsoever. And I think that kind of technology's got a really key role to play in those, exploration programs and in places where it's hard to get samples out or takes a long time to get samples out. I think that's a really key opportunity. That's where I'll be looking at it.
Yeah, portablepbb.com, I think it is. People might want to go and have a look. It's an emerging technology that's potentially extremely exciting. To be able to do parts per billion gold with a portable XRF is something I would never have thought might be possible 20 years ago. But it just may well be very, very soon. Thanks, Aaron.
Well, very good, gentlemen. We've gone a little long here, but there's been good engagement from our attendees and good questions and good discussion here. For Olympus, I want to thank you again, Dr. Gasly, for giving us some of your time here today to present on these case studies. And for everyone who's in attendance, the recording for this webinar will be available later today. We'll follow up with an email to everyone who's registered with a link webinar again on demand. And maybe we'll try to include a couple of the resources that people have asked about and include the links to those and maybe those couple of papers that you referenced about best practices. Dr. Gasly will try to pull out those references for people who are newer to the practice. They can learn from those that have been trailblazers ahead of you. So thank you all.
Very good.
Again, hope everyone
thanks
has
for having me, I should say. I really appreciate the opportunity.
Thank you.
Pleasure.
Thank you.
Have a good afternoon, everyone.